Today we're going to talk about solid-state materials. And the easiest way to begin this discussion is thinking about a linear chain of hydrogen atoms. Remember that in its simplest form, a hydrogen atom is just an s orbital, right? We have an s orbital, it can be a positive phase, negative phase, or in other words, shaded or unshaded. It has a discrete energy level at a certain position. So there's just a single line for that single hydrogen atom. If we were to take H2 as the molecule, we would have those two hydrogen atoms, each with just those s orbitals that can combine either in phase or out of phase. Remember, because we just have two s orbitals that can combine. And these form the basis of our molecular orbital diagram, where we have a bonding molecular orbital when they're both in phase and an anti-bonding orbital when one is in phase and one is out of phase. So if we were to continue to add hydrogen atoms in a linear chain, then we would have an extra orbital. Remember, a linear combination of atomic orbitals states that effectively however many atomic orbitals we have, when we make molecules, we have to have the same number of molecular orbitals. So that means for H3, so if we had H and then two H's as the outer groups, that these could form like this, or with their orbitals out of phase. We would take our orbitals and we would then be able to generate three brand new molecular orbitals. One would be bonding, one would be anti-bonding, and one would be non-bonding. So if we consider how these would combine based on our discussion previously on building molecular orbital diagrams, we see very clearly that when they're all three in phase, that makes our bonding molecular orbital. If we were to have a situation where you had the center atom was out of phase, then that gives us our anti-bonding orbital. And then subsequently, if we were to try to place an orbital in between this is what would generate our fully non-bonding orbital, because you have partially in phase and out of phase, and those cancel each other out to make a fully non-bonding molecular orbital. So that's how we get to 3. Now if we were to continue and we were to add a fourth, what we would have then is going to be 4 molecular orbitals. So if we had 2 hydrogen atoms here and 2 on this side, we would take these and generate 2 bonding molecular orbitals and 2 anti-bonding molecular orbitals. And again, remember that the ways that these s orbitals can combine are fairly straightforward because they are the same on both sides. And this one, the lowest energy one, is going to be the one where they're all in the exact same phase. The next one is going to be where you have a situation where there's a little bit of bonding and a little bit of anti-bonding, like this. Or actually, one like this is going to be this one. And then if you have a situation where you have all of these in anti-bonding mode, you would have those higher energy orbitals. So if we were to continue to build this chain, what you might start to notice is that we are adding molecular orbitals, and we're making the location between those molecular orbitals closer and closer together, such that if you were to continue this on an infinite string of hydrogen atoms, eventually what would happen is that you'd end up with a ton of molecular orbitals down at the bottom and a ton of anti-bonding molecular orbitals at the top. So again, we went from 1 to 3 to from 1 to 2 to 3 to 4 to 5 to 6 to infinity. If we were to just have an Avogadro's number of hydrogen atoms in a linear chain, this would start to produce these orbitals that become increasingly close to one another. In fact, so close that they are basically no longer discrete or quantized energy levels. And as we continue to add more hydrogen atoms, what happens is that they become effectively indistinguishable from one another. And this gives rise to what is called a molecular band, and subsequently the field of band theory, where if you have an extended solid that has generated so many molecular orbitals that they are infinitesimally small in distance and energy from one another, that they start to look more like a band as opposed to a molecular orbital. Now those generations of that band is just for a linear chain of hydrogen atoms. As you might imagine, as we start to combine this with the information we just learned about crystal structures and three-dimensional arrays of atoms, then you might imagine things would get even closer and generate even more bands. Additionally, hydrogen atoms, we were only looking at s orbitals. But in other elements further down the periodic table from period 2 and below, we have s orbitals, p orbitals, and potentially even d and f orbitals, which means that our molecular orbital diagram in three-dimensional crystal arrays is no longer going to be sufficient to think about the way that electrons populate these different states. So if we are to think about an energy diagram in terms of bands, because we have an Avogadro's number or an infinite array of atoms, and again, this was our generation of these incredibly close molecular orbitals to generate both bonding and molecular and anti-bonding orbitals, then we said that that starts to look like a band. So the way that this is typically depicted is what's called a density of states. So rather than thinking about things as a discrete quantized energy level, we'll think about them as a state. And the density of those states basically just depicts how large is going to be that band. How densely populated is that thing? And oftentimes you'll see these depicted more like this. So again, we're looking at density of states. Okay, and the further to the right along the x-axis, that means that there are more of those things populated. And sometimes they'll look like this, but more likely they're going to look like this, where you have different orbital groups. So you might think the s and the p orbitals, when they combine to form bonding or anti-bonding molecular orbitals, you're going to have a large piece that juts out into the x-axis. That is indicating effectively that there's more density at those locations. So the absolute value of that density is going to be along the x-axis. The greater the value, the more of those density of states. So that is basically the general depiction of a density of states. In addition to that, we need to also be able to think about things in terms of their electron population. So if we were to consider a density of states for some 3D crystal structure, then we would basically depict whether or not there are electrons in there by shading in that region. Rather than putting an infinite number of up and down arrows, we will just simplify our lives and actually just shade those in. So if we were to shade in this entire region, this shading is just me indicating that there are electrons located at those different states. And if I leave a section unshaded, that means that they're unpopulated bands, or in the case of molecular orbital theory, you might think of that as the lowest unoccupied molecular orbital, and these would be like the highest occupied molecular orbital. So the HOMO and LUMO is the nomenclature that we use in molecular orbital theory, but in band theory, they actually call this the valence band. So we have a valence band, because remember, we're no longer talking about molecular orbitals. There are so many that we call them a band. And the LUMO becomes what's called the conduction band. Okay, and this gets us into our discussion of materials. So the valence band is going to be where you find those valence electrons. In a perfectly no anti-bonding populated molecular orbital, you might consider that they're all in the bonding molecular orbital, and all of the anti-bonding molecular orbitals do not have any electrons in them. So we would say that this is the valence band, and the LUMO from molecular orbital theory is what's called the conduction band. And we call it the valence band because that's where the electrons are. We're dealing with valence electrons when we create molecular orbital diagrams. And it also means that the valence band is where electrons will come from when they move into the conduction band. Okay? And once that happens, you create conductive materials where you have a flow of electrons. Now let's take a look at some properties of different materials to see how band theory plays an important role. On the screen I have metals, semiconductors, and insulators. Metals are able to transport electrons at effectively any temperature, meaning that electrons can move between different density of states, and once we get a flow of electrons, we generate a current. Insulators have a small gap in between the states where electrons can move. that gap is sufficiently small that at some temperature we're able to actually transport electrons from one band to another, and this flow of electrons gives us a current. And insulators have a distance between the valence band and the conduction band that's so great that you actually cannot effectively transport electrons between those two different bands. So let's take a look at this. So for metals, for example, if we were to create on our energy diagram, if we had a valence band and a conduction band, then one of two things is true. Either this distance between the valence band and the conduction band, known as the band gap, because it is the gap between two different bands. So we have our valence band, which is completely populated with electrons, and our conduction band, which doesn't have any electrons in it. Either this distance, also known as delta Eg for band gap, the energy distance between the two bands, is sufficiently small that at any temperature above 0 Kelvin, the electrons can move between, or there may be a situation where you have a partially filled band. So either you have a very small band gap or a partially filled band gap, or a partially filled band. So if you have a partially filled band or an incredibly small band gap, then you have a metal. So here is an example where we would have a partially filled band, and this would also constitute what's called a metal. And remember, the shaded portion of these bands indicates the existence of an electron. And if an electron can move very easily from a filled state to an unfilled state, that means that electrons can flow. This gives us current. This is why we call metals very conductive. Semiconductors, on the other hand, have a band gap between the valence band and the conduction band that is, let's say, anywhere between, so this band gap is going to be greater than 0.1 electron volts, but also smaller than 4 electron volts. This means that at some temperature greater than 0 Kelvin, potentially we could excite electrons from the valence band to the conduction band. And this gets us to semiconductors. A common example of this is going to be silicon. That's going to be one of the most popular and most commonly occurring semiconductors. An example of a metal is going to be like gold, for example. So gold and copper, which is why those metals make up a lot of the wiring when we're dealing with electrical systems. Insulators, on the other hand, have an incredibly large gap between the valence band, which is the fully populated band with electrons in the valence band, and the conduction band. So if this band gap is sufficiently large, specifically if this band gap is greater than 4 electron volts, then the likelihood that an electron will be energetically excited by heat from the valence band to the conduction band is going to be incredibly small. Now this brings up another important concept called the Fermi level. The Fermi level is the highest energy level that electrons can exist for any given material at 0 Kelvin. On the screen, I have gone in and drawn in where the Fermi level is for all metals, semiconductors, and insulators. Notice that the Fermi level for a metal always cuts through a band. This indicates that electrons can exist within that band. And if electrons can exist within that band, even at 0 Kelvin, that is going to rigorously define what a metal is. This means that electrons can very easily transport between those different energy states, and that is going to give us a very conductive material like copper, silver, other examples of different metals. Semiconductors, remember, have that small band gap, or the energy difference between the valence band and the conduction band, or in other words, if you think about this from a molecular orbital standpoint, the energy difference between the HOMO and the LUMO. If that is sufficiently small, then somewhere in between is going to be the highest energy level at 0 Kelvin that we are likely to find an electron. But remember, we are usually in the universe greater than 0 Kelvin, which means that at 0 Kelvin, here is where we're likely to find the highest energy electron, because electrons are constantly moving, that at some temperature above 0 Kelvin, there's going to be a likelihood that those electrons will actually move between the valence band and the conduction band. Similarly, for insulators, the Fermi level lies in between the valence band and the conduction band. However, because the band gap, or the distance between the valence band and the conduction band, is so great, the likelihood that at most temperatures above 0 Kelvin, unless we get incredibly hot, that there are not going to be any electrons that can transport between the valence band and the conduction band. So what can we do to make materials a little more like a conductor or a metal, or potentially more like an insulator? And for this, we need to think about what's called doping. Let's talk a little bit about silicon. Remember that silicon is, just like carbon, has 4 valence electrons in its valence shell of orbitals. So if we were to think of a 3-dimensional array of silicon, we would start with a single silicon atom that has 4 valence electrons around it. This is the Lewis symbol for silicon. And if there were a silicon atom to the right of it, it would share an electron. If there were a silicon atom below it, it would share another electron. And if there were a silicon atom to the left, it would share another electron to pair up. And if there were a silicon above it, it would share, again, an electron. And this would, if we were to hone in on that center silicon atom, it would fill the valence shell of electrons, thus satisfying the octet rule. Notice these 4 different pairs of electrons indicated by dots, and this is essentially how you can think of a 3-dimensional array of silicon atoms. So remember, this is a semiconductor where the band gap between the valence band and the conduction band is sufficiently small that electrons could potentially, above some temperatures above 0 Kelvin, could potentially transport between the valence band and the conduction band. And if we were to substitute one of these other atoms, so I'm just going to redraw this, my silicon atom, and I'm just going to substitute one of these, so I'll draw the 3 others here. And if on the one on the right, if I were to instead put in something like phosphorus, phosphorus is on the 3rd row of the periodic table. It has 5 valence electrons. This means that it would have one to pair up with that silicon. It would have another up there, one down here, and it would have 2 down here for a total of 5 valence electrons. This means that there is an extra electron. We are no longer just satisfying the octet rule, but we're providing an extra electron. And that electron is negatively charged. And now that we've provided an extra electron, what that means for our density of states is that there's actually going to be a few more electrons that would go into that conduction band. So if we had a single phosphorus atom, it would be 1 electron. If we had 20 phosphorus atoms, it would be 20 electrons. But some number of electrons is now going to be populating that conduction band, which was previously unfilled. This also raises the Fermi level to where it now cuts in between one of the bands. And that means that it is now acting more like a metal, because electrons can very easily move in between filled states and unfilled states. And the movement of electrons and the ability to change between different states is what gives rise to conduction. So this means that we are enhancing the conductive properties of silicon by doping it with a phosphorus atom. Now let's consider an example where if we were to again have our 3 silicon atoms in the original positions as in our first example, but instead we were to place something in like boron. Boron only has 3 valence electrons. Remember, it's 1 to the left of carbon on the periodic table. This means then that it doesn't have an extra electron to pair up with silicon. In fact, what it leaves behind is what's called a hole. So a hole is going to be effectively a vacancy of electrons, and we assign it a positive charge. And the way that we can think about that on our density of states diagram is like if we removed some of the electrons from the top of this valence band. And if we have removed some of those electrons from the valence band, then what we've done is we've actually lowered the Fermi level. And if we lower the Fermi level to a position where it cuts through a band, now we have electrons that can transport between lower energy states to higher energy states with relative ease, because effectively the difference in energy between these filled and unfilled states is zero. And now we've also enhanced the conductive properties of silicon by doping it. And since this leaves behind a hole, which is effectively thought of as an electron vacancy or a positive charge, we call this p-type doping. Similarly, when we doped silicon with phosphorus, we added an extra electron. Electrons have negative charges. We call this n-type doping. And this gives rise to the two different types of doping mechanisms we're going to talk about in this class. That's n-type doping, where we have generated extra electrons to populate the conduction band, and p-type doping, where we have removed electrons from the valence band. Both of these dopants and both of these doping types enhance the electrical conductivity that silicon as a semiconductor had in its natural state. Now let's consider what might happen if you were to bring together and actually touch a p-doped semiconductor and an n-doped semiconductor. What would happen is you would actually generate what's called a diode. And a diode is a device in which a current flows in a single direction. Remember, according to the law of electrostatic attraction, negative and positive charges are attracted to one another, and current is going to flow from the negative side to the positive side. So the electrons are going to be attracted to those holes that we talked about. Remember that in p-typed semiconductors, you've generated holes, you've lowered the Fermi level from its original state. In n-type semiconductors, you have raised the Fermi level because you have added extra electrons. So remember, on this side is where you're going to find your electrons. Your electrons will be on this side, and your holes will be on this side. So here's a hole, here's another hole, and another hole. And if we were to bring those two together, what's going to happen is we're actually going to connect these two. So when we connect those two, these electrons are going to flow in the direction of those positive holes to fill those vacancies. And also what's going to happen is drift is going to occur where the positive charges are going to build up on the right-hand side. Now, if we were to just take a p-type semiconductor and an n-type semiconductor and bring them together, eventually all those electrons that were extra on the n-type would flow over to the p-type semiconductor. And this would eventually stop, and it's only in a single direction. That single direction would eventually stop, which is why we have to connect electrical devices to some current and voltage driving mechanism, like a battery, for example, to regenerate those negative charges. So in our class, what we're going to talk about is more of these types of devices and how we actually generate solar cells, how we generate photodiodes which detect light, or how we generate light-emitting diodes, like the ones made up on the lights, to create this light board, or the lights or the images that you see on a cell phone or a television. And this is why solid-state materials and your understanding of where electrons are in three-dimensional arrays is so important, because it plays such a tremendous role in everyday society.